Hi, so we continue our lesson to half-life, right? So what is half-life? Right, half-life is the time taken for a sample of radioactive nuclei to decay to half of its initial number. So time taken here can be either in years, in weeks, in days, minutes, or even in seconds. Okay, so it will decay into half of its initial number. So the initial number can be either the number of atoms or its mass or percentage, right? Now, the table here shows that the red nuclei is the radioactive nuclei that has not decayed. Okay, this is the initial mass, right? Okay, and the white nuclei is the decayed radioactive nuclei. So after half-life, the first half-life, it will become half of its initial mass. So it will become 50% left or remains. So another 50% had decayed. So after second half-life, all right, only quarter nucleus remains compared to the initial mass or initial number of atoms. Alright, so on and so forth. So we continue to radioactive decay. So remember what is radioactive decay? So it is a random and spontaneous process of unstable nucleus to become more stable nuclei by emitting alpha particle. So this is the symbol for alpha particle, beta particle, and also gamma ray. And don't forget that it releases a large amount of energy. Example 1, the half-life of zinc-17 is 2.4 minutes. If the initial mass is 100 gram, how many grams will be left after 7.2 minutes? Alright, so initially we have 100 gram of radioactive sample, and then after first half-life it will become 50%. So can you guess how many gram left? Yes, it is 50 gram after half-life. And after another half-life, can you guess how many gram left? Yes, exactly. After another half-life, so it will become 25 gram. Alright, and then after the third half-life, how many grams will left? Yes, it will become 12.5 gram. So we can add all the half-life, so 2.4 minutes plus 2.4 plus 2.4 minutes, so we'll get 7.2 minutes. So 7.2 minutes equal to 3 half-life. Okay, and so the remaining, okay, of the radioactive nuclei is 12.5 gram. Okay, next example 2, palladium 100 has a half-life of 3.6 days. Okay, so previous question in minutes, so this is in days. If one had 6.02 times 10 power of 23 atoms at the start, how many atoms will be present after 80.0 days? Right? So initially we have 6.02 times 10 power of 23 atoms. Right, after half-life, it will become Y number of atoms. After 3.6 days, after the second half-life, become W number of atoms. And after its third half-life, it will become X number of atom. And after the fourth half-life, it will become Y. And after 5 or fifth half-life, it will become Z percent or Z number of atom that left. Alright, now, so we change, okay, the unknown to percent. Okay, so after fifth half-life, right, after fifth half-life, so the only percent that left is 3.125%. So we change it in a decimal fraction after 5 half-life. So it becomes 0.03125, and then we times 0.03125 to the initial number of atom. So the answer will be 1.28 times 10 power of 22 atoms remains. Next, decay series. Alright, I introduced decay series so that we have another option. Okay, we have other option to solve problems related to nucleus that decays. Okay, the concept of half-life can also be expressed in the form of a decay series as follows. So N naught, okay, N naught is the initial mass. Okay, after half-life, the mass or percentage or number of atoms will become half of it initial mass, and then after half-life it become quarter and so on. Now, number of radioactive nuclei that has not decayed, N, equal to half. N is the power of N, alright, times N naught. Okay, so N naught is the initial mass. Okay, N naught is the initial number of radioactive nuclei, N is the number of half-life, and half T is the half-life of radioactive substances. So let's see how we can apply the decay series to solve problems related to substance which has decay. So this is the same example as the previous one, example 2. Alright, so palladium 100 has a half-life of 3.6 days. If one had 6.02 times 10 power of 23 atoms at the start, how many atoms present after 18 days? Alright, now solution. So this is the equation, right? Number radioactive nuclei that has not decayed, N equal to half power of N and naught. Right? So N equal to half, right? Okay, so remember that it is the fifth half-life, alright? And 1 over 2 power of 5, we will get 1 over 32 times the initial number. So we will get 0.03125 times 6.2 times 10 power 23 atoms, and we get final answer as 1.28 times 10 power of 22 atom remains. Alright, now example 3. Okay, by using decay series, after 24 days, 2 milligram of an original 128 milligram sample remains. So solution, number of radioactive nuclei that has not decayed, N equal to half power of N and naught is the initial mass, alright? So the decimal fraction remaining, alright, 2 milligram over 128 milligram. So, right, N is the remaining, okay, number of radioactive that has not decayed, N. Alright, divide by N naught. N naught is the initial mass, alright. So we get the decimal fraction remaining. It is 0.0156252. So we put here, okay. Alright, next, find the half-life N. So we must find N since we have the decimal fraction. So half N equal to 0.0156225. So mathematically, N, okay, and you put here log half, which is 0.5, equal to log 0.015625. So n equal to log 0.5 divided by log 0.015625. So we get n equal to 6. So 6 half-life for the 128 gram sample to become 2 milligram remains. Alright, now determine the half-life. So 24 days divided by 6 half-life. So the half-life of this sample is 4 days. Next, radioactive dating. So radioactive dating is one way to determine the age of a rock. So look at the diagram here. So we have newly formed rock, right? We can see that this rock contains uranium 100%, alright? The same rock sometimes later, okay, it is not 1 or 2 days, it can be a month, a year, or maybe 100 of years, right? So we can see that some of the uranium had turned into lead, alright, maybe 50%. And after some years, or 100 years, or 1,000 years later, the same rock, okay, we can see that uranium had decayed and become. The half-life of uranium-238 is 4.5 billion years. Okay, it decays into radium-226, which in turn decay into radon-222. Okay, and then radon-222 becomes polonium-210, which finally decays into stable nuclei, which is lead. Alright, lastly, radioactive decay curve. So this is an example of radioactive decay curve. So we can see that at the y-axis is the number n of mass or number of atom or percentage of remains of radioactive nuclei, and at the horizontal axis is the time. Alright, so we can see that, okay, as time increase, the number of percentage decreases exponentially. Alright, so as we compare a different radioactive nuclei, okay, so we can see that for the orange radioactive substance, it has higher rate decay and it has shorter half-life. So when it has shorter half-life, so it has higher rate decay. So compare with a green, okay, nuclei, so it has a higher half-life, so it has lower rate decay. So that is the relationship between half-life and also the rate of decay. That's all for now. Okay, we continue to next lesson.